Okay, so let's remind ourselves about the general form of a weak acid. Remember, acids provide H plus in solution. If it's not one of our 6 strong acids, then it's a weak acid. And in order to be an acid, we'll put it into water. The double arrows indicate weak acid, meaning that some dissociates, but usually the equilibrium lies far to the left. In order to be an acid, let's remind ourselves, when I say acid, what are you supposed to think of? So an acid is H plus. And let's remind ourselves, hydrogen has 1 proton and 1 electron. In order to become H plus, it gets rid of its electron and becomes just a proton. So sometimes H plus is referred to as a proton. So he has 0 electrons. He is electron poor, so he must be an electron acceptor. All he is a proton. He's got nothing else but a proton, so he is a proton donor. A base, on the other hand, has to be opposite of that. So bases are OH minus. They are electron rich. Therefore, they're electron donors, which is, notice the opposite. Once you figure out what one of these are, I always start with H plus and remind myself that H plus has no electrons. So it must be an electron acceptor. And he is a proton acceptor. So an acid is a proton donor, so he's going to get rid of an H plus. After he gets rid of an H plus, he will simply be A minus. And the H plus is going to go to H2O, so it's going to be H3O plus. This is the general form for a weak acid. Now, let's go over the general form for a weak base. We'll put that base into water. He's going to accept a proton from H2O. So he's going to become BH plus, and he's going to leave behind OH minus. Does everybody follow that logic? So this, in this case, is my base, leaving water to act like an acid. And this is my conjugate acid and my conjugate base. The stronger a base is, the weaker its conjugate will be. The weaker a base is, the stronger its conjugate will be. So here's what it looks like. Water can either act like an acid or a base, and you're seeing both of them. This is both situations. So let's go over the conjugates. This guy is super, super, super strong. Therefore, his conjugate is going to be the weakest. So this one is the strongest acid you can have, and this is the weakest base you can have. Down here, water is the weakest acid you could have, therefore its conjugate is going to be the strongest conjugate base. So when you say, well, how do I compare that? Well, you can look at the acids. For example, you can look at our list of Kas. You'll see that, let's just find nitrous acid, HNO2, and hydrofluoric acid, HF. Nitrous acid is a stronger acid than hydrofluoric. Therefore, hydrofluoric's conjugate, which is F minus, will be stronger than nitrous acid's conjugate, which is NO2 minus. So you guys see the arrows up there and how it indicates the strength? So that's how you determine whether an acid and its conjugate are strong or weak. So let's do some example problems with bases. We're going to do weak base problems now. Remember, there's a couple videos of weak acid problems if you need to remind yourself how to do it. So a problem might look like this. Now, if they did not give you the KB, you can look that up. So we went over acid dissociation constant. Now let's go over base dissociation constant. It's a similar concept. They are related to each other. So by KW. Does anybody know what KW is? Well, let's remind ourselves what neutral water would be. Remember, neutral water has a pH of 7. So what's the concentration of H plus if the pH is 7? Power of hydrogen. So if the pH is 7, the concentration is 1 times 10 to the minus 7. If the pH is 7, what's the POH? 7. What's the concentration of OH minus? That's a pH neutral solution of 7. So you can rearrange this formula and say that KB is equal to KW divided by KA. KA is equal to KW divided by KB. And KW is always 1 times 10 to the minus 14. It is a base. If you are unsure, see what he looks like, see which looks more common. If ammonia acts like a base, he accepts a proton, he'd be NH4 plus. Does that look familiar? Yeah. If he was an acid, he would donate a proton, he'd be NH2 minus. That doesn't look as familiar, does it? So the other thing you can look at is the KB. If the KB is smaller than 1 times 10 to the minus 7, then it's an acid. If the KB is greater than 1 times 10 to the minus 7, it's a base. Okay, so let's do the general form of this equation. When you put NH3 into water, oops. He's going to act like a base, meaning he's going to accept a proton, so it'll be NH4 plus, and he's going to leave behind OH minus. Remember, if it's not a strong base, then it's a weak one. Can anybody name a strong base? OH minus. So if you're looking at the chemical formulas, what would you be looking for? OH is a good one. It's got to have OH on it. When you're looking for chemical formulas, it's going to be group 1 or group 2 metals. So alkali metals or alkali earth metals with a hydroxide, those are our strong bases. Any other base is weak. So sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, anybody from the first 2 families or columns with a hydroxide are strong. Everything else is considered weak. So remember with ice charts, the initial is going to be before any dissociation occurs at all. And then obviously we're going to have a minus X plus X plus X. So if you remember what we talked about beforehand, 0.15 compared to the value of x is going to be a large number. The value of x is going to be a super small number. If the value of x is going to be a super small number, it's not going to change that 0.15. So now we can do KB is equal to products over the reactants, which would be x squared over 0.15. And remember, we're going to ignore the contribution of that x. So the general form of KB is going to be the same as KA, which is x squared over initial concentration. The only thing you have to be careful of is, did they give you Ka or Kb? If it's a base and they gave you Ka, you first have to calculate Kb. And obviously we know a good way to check ourselves is if it's a base and you get a pH less than 7, you've made a mistake, right? Okay, so let's fill in the numbers we know. It's 1.8 times 10 to the minus 5 equals x squared over 0.15. So let's rearrange and we'll get a value for x of 1.643 times 10 to the minus third. Be careful though, in this situation, x is not the concentration of H plus. X is the concentration of OH minus. So if I do negative log of x this time, what am I going to get? But I'll get the POH, right? So I do negative log of 1.643 times 10 to the minus third in my calculator, and I get an answer of 2.784. Now that we've got acids that we learned the week before spring break and bases that we're learning now, make sure that you're asking yourself if it sounds reasonable. Obviously, I can easily get the pH because pH is 14 minus POH, or 11.22. That is a base, that makes sense. So if they asked you for the pH, the answer would be 11.22. Remember, the given was, and I'm pointing this out to you so that you recognize what's going on here. This given here has 2 sig figs. That corresponds to the 2 decimal points after the decimal. So methylamine is CH3NH2. And KB is 4.4 times 10 to the minus 4. This might be a little tougher to decide whether it's an acid or a base. But I'm going to tell you right now, when you look at amine, amines have nitrogen in them. I want you to automatically think of nitrogen as electron rich because he has a lone pair of electrons above him. So in this case, he is going to act like a base. You can also see that KB is greater than 1 times 10 to the minus 7. Therefore, it's going to be a base. So let's try to do this one without an ice chart and see if you catch the drift. I'll still do the equation for you so you make sure that you see what's happening with a base. You're going to take the base and you're going to put it in water. Acting like a base, he's going to be a proton acceptor. Remember, acids are protons. That means bases are protons acceptors. That means that he's going to take in H plus from water. So one more H and one plus sign is going to leave behind a hydroxide, like such. I can remember the general form is Kb equals x squared. It would be initial concentration minus x, but we're going to ignore the contribution of x because it's going to be very small. So you do not need to do an ice chart or all of the work for each and every one of them once you understand what's going on. Try not to skip steps until you're pretty good at this. So I'll solve for x, and I'll get an answer of 0.1625. I'm going to remind you what we really should do, what you will do next year is you will have to do the 5% rule. We don't necessarily have to do the 5% rule here because I'm not going to give you any problems that do not pass the 5% rule. But if I was going to do the 5% rule and see if it's really kosher and legitimate that I ignore the contribution that X makes, I would say I want to compare X to the initial concentration to see if it is within 5%. So 0.01625 over the initial concentration of 0.6. And let's do the 5% rule. And I get 2.77%. No, 2.71%. That is less than 5%, so I'm good to ignore that. Now, double checking though, if you skip the ice chart, you have to remember X is not concentration of H plus, it is concentration of OH minus. So negative log of 0.01625 is going to give me POH. It's going to be 1.789, and then pH is going to be 12.211. But this is another kind of problem where they might ask you to calculate the initial concentration. So let's write down what we do know. If we don't, we can look it up, which is the Kb for ammonia. The Kb for ammonia is 1.8 times 10 to the minus 5. Let's see all the things I can calculate from this. I can also calculate the Ka if I needed it. And that would be Kw divided by Kb. Or 5.56 times 10 to the minus 10. If the pH is 12.16, I can do, in your calculator, you would do inverse log, so second log of the negative pH, and I get a concentration of H plus, if I needed it, of 6.92 times 10 to the minus 13 molar. I can also get the POH, which would be 14 minus the pH. Or 1.84. Now, there's two ways that I could calculate the concentration of OH. I can remember that the concentration of H plus times the concentration of OH minus always multiplies together. Let's write down our formulas just to remember. I'm going to get your AP, so we're not writing down formulas we're not allowed to use. So from your AP reference packet, make sure you know what's going to be given to you so you don't try to use things that were not given to you. Here we go. So Kw is equal to Ka times Kb. That's also equal to concentration of H plus times the concentration of OH minus, also equal to 1 times 10 to the minus 14. So I could either say that OH minus is Kw divided by H plus. I could say OH minus is the inverse log of the negative POH. So I do second log negative 1.84. So at equilibrium, the concentration of OH minus is 0.01445 molar. So now we know that that is also the value of X. So Kb is equal to X squared over the initial concentration minus X. So let's fill in what we know. That's our general form. Kb is 1.8 times 10 to the minus 5. X is 0.01445 squared. And then we get initial concentration minus 0.01445. Remember what I said, there's no sense in ignoring X if it's given to us. And I get initial concentration of 11.6 molar. Okay. Now, here's what I'm going to warn you of. Both problems are done so similarly. There's just a little bit of difference. You got to remember if X is the concentration of OH minus or the concentration of H plus. You got to remember the difference between Kb and Ka. You got to know the relationship between Ka and Kb. All the formulas are in your pink packet, so make sure that you recognize where to find them and how to use them. And I know that was a lot to fill our brains with for today.